Hello students. In this video we're going to compute the volume of a solid, and that solid is created by revolving a shape around a horizontal line. And in this case, where the shape is going to be determined by the region bounded by the vertical line x equals 1, the parabola x squared plus 2, and the line 2x plus 5. And then we're going to revolve that around the line y equals 12. Now, if that seems like a lot of information to carry around in your brain, and you are having trouble visualizing that, that's fine. So do most people. So we're going to have to draw a picture. So let's do that and set up our integral for this for computing this volume. All right, so first thing I'm going to do is I'm going to draw the line y equals 12. That's easy. That's just a horizontal line. 12. Vertical line x equals 1. That's easy. We're just going to draw that vertical line. And then 2x plus 5, let's see. That's going to be above x squared plus 2. And we could tell that, by the fact that x squared plus 2, right, its intercept is over here at 2, 0, 2. And the intercept for the line is here at 0, 5. So they start out, going like, 2x plus 5 starts out here and makes its way this way. And then the parabola is curving up, and then they meet at a point. We have to determine that point, okay? So we'll get there, and we'll determine that point by the point of intersection is, of course, intersect means where the curves meet, and the curves meet when they're equal to each other. So that'd be when x squared plus 2 is equal to 2x plus 5. All right, we'll do that momentarily. Let's plant a flag in this and get to the revolution and what the surface is going to look like. Here is one shape. It's like a pincer for a crab pincer or a lobster pincer. And we're going to take that shape, this somewhat curved triangle, and it's going to be revolved around this horizontal line. Now this could be axes, this could be the coordinate axes, the x-axis, it could be the line y equals 12. It doesn't matter. The principle is still the same. And as it's revolving around this horizontal line, you're going to get this solid of revolution. And it's going to look something like if you ever took the filler of a pen out of that pen, what that the tip of the pen would look like without the pen part in it. It's kind of how I visualize it. But anyways, the point is you're going to get this little washer, and let's separate that out here, and let's break it up into a little bit of thickness. And remember, in integration, that's what we do. That's the process of integration. We break things into little parts and then we add them all together. So this is what we expect the washer to look like. Okay, so this is how we're gonna, this shape is how we're gonna set up our integral. So let's find that point of intersection. So x squared plus 2 equals 2x plus 5. If I push the 2x over, I'll get a minus 2x. If I push the 5 over, I'll have 2 minus 5, which gives me a minus 3. This factors, let's check that. X squared minus 3 plus 1 is minus 2x, and minus 3 times 1 is minus 3. And so that means x equals 3 is one point of intersection, x equals minus 1 is the other, but x equals minus 1 is out over here, so we can ignore that. So x equals 3. So when x is 3, if I plug 3 into the line, for example, I'll get 11. If I plug 3 into the parabola, for example, I'll get 9 plus 2 is 11. So that is indeed the point of intersection. Now, because we're revolving it around the horizontal line, our inner radius and our outer radius are going to look a little bit different. Now, the inner radius, right, that's, when you think about this as the axes, you just think of it as the distance between, the line and this axis. And same thing with the outer radius. Well, now the axis is the line y equals 12. As before, the axis, a lot of times was y equals 0. That's all right. The strategy doesn't change. Just the strategy is still the same. How we execute it is going to be a little bit different. And then this washer is going to have a little bit of thickness. We'll call that delta x. Okay, so let's focus on the inner and outer radius. So the inner radius, since this is just like area between curves, right? You have a top and then you have a bottom, which is the top here is the line, the bottom here is the line 2x plus 5. So the radius here will be 12 minus this red circle, right, which is actually created by revolving this line around. So it's going to be 12 minus 2x plus 5. Similarly, the outer radius is going to be 12 minus the parabola. So it'll be 12 minus x squared plus 2. So the technique is really similar to what you did before with area between curves. So I'm going to call this inner radius Ri, and I'm going to call the outer radius Ro. And it's, again, the strategy is still the same. It's going to be pi r outer radius squared minus pi inner radius squared times the thickness of the washer, delta x. When you multiply this area times its little height here, the thickness of the washer, you get the volume of the washer. Notice that in general, this principle applies, and it's the same principle as when we revolve this shape around the x-axis as when we revolve it around the line y equals 12. I know I keep repeating that, but really the strategy is still the same, and that's important for you to keep in mind. Okay, so let's do the arithmetic necessary to finish the problem up. So we have the volume of the washer we derive from here, right? It's this area times this thickness. That gives us the volume of the washer. So we'll have to plug in those values here. And this picture is here just to remind you of what we had done from the previous slide, because I needed to clean it up, make some room. So the outer radius was 12 minus the quantity x squared minus 2. What I'm going to do is I'm going to distribute the minus 1, and I'll get a 12 minus x squared and a 12 minus 2. So 12 minus x squared and a 12 minus 2. Then we have to square that radius. Similarly, it's going to be a 12 minus 2x and a 12 minus 5. So it's 12 minus 2x, 12 minus 5. And that radius, the inner radius, has to be squared. So it's pi r squared. Now I'll just clean this up. 12 minus 2 is 10. 12 minus 5 is 7. So now I have 10 minus x squared, quantity squared. And I have 7 minus 2x, quantity squared. And I'm going to factor the pi out. Since that's not being squared, I'm just going to park the pi out here. And the delta x will stay parked out there. So then if I square this, I'll have 10 times 10 is 100. Then minus 10x squared, the inner terms will be minus 10x squared is a minus 20x squared, and then a minus x squared gives us a plus 4x squared. I'm assuming at this point in a calculus class that you know how to FOIL out a binomial. And then similarly, 7 times 7 is 49, minus 14 is minus 28, and minus 2 times minus 2 is plus 4x squared. And then I'm going to distribute this minus 1 into this quantity here. So minus 49. So 100 minus 49 is 51. Minus 28 is a plus 28x. And then I have an x squared here, so I'll have a minus 4x squared. So minus 20x minus 4x squared is a minus 24x squared. And then I have an x4 squared. So take a moment and make sure that you can go from this setup here to this step, to this step, to this step, to this step. So if you have to pause the video, make sure you can follow along and get this part right. This is really, a lot of times, the most difficult part of the problem for students. It's setting it up and then doing this algebra. So this is the area of the face of this washer times the thickness. So we're implementing something called Cavalier's principle to do this. And that's just a fancy way of saying we're multiplying the area of this surface here, this washer surface, times the thickness. Okay, I'm going to continue now. So now that I have this area, this pi r squared, so to speak, times delta x, I'm going to compute the total volume by, Riemann sum, right? So I'm adding up all of these areas and times these little delta x's. So I'm adding up all the washers together, okay? And this sum symbol means I'm adding up all the washers, and then I'll be taking an infinite number of those washers. And this delta x will get smaller and smaller as I refine the approximation. You don't have to think about it this way. I'm just reminding you this is what we're doing. What you can now realize is that this area, times this thickness, right, this is what's giving us the integrand for our integral. And remember, we're going from the vertical line, x equals 1, to the point of intersection, x equals 3. Right? That's it. So let's do that integration. So I just recopied that integral up here. This is our volume now. And now it's just a integration problem. So I integrate 51 and get 51x. I get x squared divided by 2, so 28 divided by 2 is 14. X cubed divided by 3, 24 divided by 3 is 8, and then there's the minus sign there. And then x to the 5th divided by 5. And then I'll be integrating from 1 to 3. So I will just plug in the 3 into each of these terms. And then I'll plug in the 1 into each of these terms, and I'll subtract the difference. I'll leave the pi parked out in front. You do this arithmetic, and you get a volume of 272 over 5 pi. All right, so just keep in mind what we've done here. We set up an area, which was a pi outer radius squared minus pi inner radius squared, and that was how we got this pi and then this term here. Then we multiplied that by the thickness of each little washer. Then we added all the washers together. That's the integration. We found the point of intersection, x equals 3, and this x equals 1 was a vertical line. That was given to us. That was part of the setup of the problem. Then we just performed this integration. We did so here. We did the arithmetic, and we got the volume. Good luck.